In the next few videos, we will discuss the vector product. There are three different ways to multiply vectors: a product by scalar, dot product, and finally cross product. Having this random vector r, multiplying this vector by a scalar quantity of 3. This is like replicating the vector 3 times. The resultant vector is 3 times the original one. Now dividing the resultant by 2. The first thing to notice is that the resultant of the dot product is a scalar quantity. You may think of a dot product as of how much one of the vectors is contributing in the direction of the other vector. So when these two vectors are in the same direction, then the contribution of each one into another will be maximum, and it will be 0 when they are perpendicular to each other. In short, we can say that this product is dependent on the angle between these two vectors. We will try to visualize what we just said in these 4 situations. In the first case, the two vectors are in the same direction, so they have maximum contribution. While in the case of the 30 degrees, the contribution area will shrink a little bit. The third case of 70 degrees, the contribution is even smaller, and finally shrinks to 0 in the fourth case when the angle between the vectors becomes 90. Think of these shaded areas as the amount of projection of each vector into the other. So in the first case, the yellow vector will be fully projected into the black one beneath it, while in the last case, the red vector will not be projected at all. Now we can define a formula for the dot product. Notice that it depends on the magnitudes of the two vectors and the cosine of the angle between them. Now finding the dot product of the 4 cases and comparing them, we can see how the value of the dot product decreases as the angle between the vectors increases, and finally becomes 0 when the angle becomes 90. Look at these vectors, how they dot product with the black vector. The blue vector will do maximum product, while the green and red are 0. And finally the yellow vector will do a negative projection as it is opposite to the direction of the black vector. Let's try dot product these two vectors. First we need to find the angle between them. We see that the result of this product is negative, and this is because the angle between the vectors exceeds 90 degrees. So the projection of one vector into another will contribute a negative value. Imagine it as that the blue vector can be projected into the red vector only if the red vector is rotated 180 degrees. Let's move to discuss vector projection. What we have just seen is one vector rotating toward the other vector until it coincides with it. And this is not the vector projection. While what we see in the next case is that the black vector is projected into the red vector. We can see that there is a difference between rotating a vector and projecting a vector. We use this formula to calculate how much of the black vector B has been projected into the red vector. With a few steps of simplification, we conclude that the component of the black vector into the red one is simply the cosine ratio of the theta angle of this right-angled triangle with the amplitude of the black vector as its hypotenuse. One more point to notice is that this component is just a value. It's a scalar quantity. But the direction of this component is already known. It follows the direction of the red vector as it resides within it. And to mathematically define this direction, we simply multiply this component by a 1-unit value of the red vector. Now let's project the vector c into a vertical and horizontal components projected onto two unit vectors of an amplitude of 1. Before we project them, we can expect that the vertical component will have greater value than the horizontal one. Drawing these two perpendicular lines can help us visualize these components. Comparing these values, we can see that the original amplitude of the vector is 2, while the projected vertical component is 1.88, and the projected horizontal component is 0.68.